Okay, thank you. I just want to introduce my co-authors, Ali and Cheppy, and Paul Tourney, who's the president of our company. What I'm going to talk about today, at least try to get through in the time span, is approaches for predicting service life. Two of them that are out there, FID Bulletin 34 and ACI 365 1R, and then and also 365 committee is working on another standard for designers. Models available for estimating and predicting service life. We're going to look at Life 365 model, which was discussed a little bit. Duracrete, which is used as one of the models in FIB 30 and FIB. Stadium model, and we have a new service life model that we'll talk a little bit about too. We compared results for a bridge deck, and then we'll look at some other examples with cracked concrete multi-layer system analysis. Now, if you're going to be specifying 100 years plus design life, or matter of fact, for any design life, you should define the service life, and that should be, and things you should have in there is time to corrosion initiation, time to first repair. If you can do a probabilistic approach or deterministic, you should state that. You specify exposure conditions, specify the maximum water to cementitious and minimum covers and tolerances. What SCMs are you allowed to use? Specify acceptable reinforcement types. Specify if you can use corrosion inhibitors or if they're allowed. Specify overlay properties if you're using that. Talk about surface treatments if you're going to use them. You should say something about maximum acceptable crack widths and densities, which hasn't been mentioned up until now. And specify acceptable models to verify that the design will meet the service life. And you gotta watch your model, what it puts for limits on hydration time, because concrete will not continually hydrate forever. FIB Bulletin 34 is a comprehensive guide to address service life of concrete. It addresses a probabilistic approach. However, some damage is addressed by, you can adjust it by correcting for it up front. Like ASR, for instance, you would use aggregates that aren't susceptible, sulfate attack, and then it uses a probability approach for corrosion. You can provide exposure boundary conditions, basically based on European empirical results, which are might be a little bit different than what we would say in the US and North America. Possible aging time bias due to changes in cement chemistries. A lot of the long-term information is based on some concretes made with cements that we don't use today. Suggest a Fickian approach to chloride ingress and make simplifying assumptions for chloride ingress in non-water saturated concrete. Provides threshold values for black steel, but not other systems at this time. The Duracrete model, as mentioned, is used, and in the case of 365 1R, it can be used for a guide for more rigorous models of chloride ingress. So, more rigorous models, such as Stadium, will also meet the requirements of the FIB model. It provides environmental related, 365 1R talks about environmental related failure mechanisms and guidelines to address them. It's more than just corrosion. We also have sulfate attack, alkali area reactions attacks, freezing and thawing, chemical attack. We're going to concentrate mostly on corrosion today, but these other things have to be taken into account when you're designing for a long design life. It does give examples of various techniques to predict performance, field assessments, how you make an economic analysis, models to be discussed, all the models that we're discussing today will do follow its guidelines, and it's working on a more definitive approach right now. If you're going to talk about service life and design, it's good to have a good idea of what we're kind of looking at. 2D was one of the first guys to look at it. There's been modifications of this model, but this is a pretty good model. It has damage on the y-axis, and then it has time. And typically, you're going to have like an initiation time, then you have a propagation period, and then you get to the end of serviceability. Other times, you might get to the end of serviceability, but you say repairs are acceptable at that point, and then you can get more service life with the repair, and eventually get to your design life of the structure. It can either be here or here, depending on how you define it. Typically, for hard to reach components, you're stopping over here. So if you have substructure components, you might want here. A deck might be over here. You can easily get to it. Service life modeling, all these, to some extent, your models have to look at this. So you look at exposure conditions, and that would be chloride, sulfates, alkali loading, moisture, temperature, geometry, concrete cover, corners, joints, surface treatments, reinforcing systems, various types of bars that can be used. And now you even have some bars that are combinations of those. Concrete materials, cement, SEM chemistry, aggregates, and admixtures. You got transport properties. These, some models, they just tell you, they give you predictions for them. It's better to measure them directly because materials do differ. ASR susceptibility and freeze-thaw resistance are things you need to address. You have the various models, whichever model you're using down below over here. You can feed all this information in there. You can get something out. At this point, you have to make an engineering assessment of what the propagation time might be after initiation. How much damage do you want to take care of? You can go back and do more iterations and change things. Life cycle cost analysis is important. You can all build a system that would last a long time and cost a lot of money. The real key here is to get something that meets the design life, but without that excessive cost. And once you get that, you make recommendations to the owner and to the design professionals to get this incorporated into the job. I'll talk about the specific models. Life 365 models based on Ficks second law of diffusion, uses bulk diffusion, uses variable chloride surface buildup to simulate at non-saturated conditions. But boundary conditions are based on some limited field data in North America. I think, as just shown by Doug, some of the surface loadings on chlorides are a little bit on the high end. Considers reduction of diffusion coefficient time based on the SEM content of the concrete, and it does that for a default up to 25 years. It is adjustable. The defaults don't address differences in cementitious materials or total amounts of cementitious added. So you might use it initially to get an idea. You really need to determine the concrete properties for the materials you're actually using. There's a probability analysis based on a study by Bentz, which shortens the time from running Monte Carlo. And it has an economic analysis so you can calculate life cycle cost. And I think it brings it down to net present day cost, which is important. The Duracrete model, which is outlined in the FIB Bulletin, is also based on Ficks' second law of diffusion. Non-water saturated concrete is addressed with assumptions on surface chloride and outer layer to be discounted. Basically, you take off a little bit of the surface layer to account for the wicking. Time-dependent diffusion, but no end of decrease within 100 years. If you have good cover and a lot of SEMs present, a high quantity of SEM, you could overestimate performance in some cases. This is especially concerned with, as I mentioned, with SEMs, and in some cases where people did some benchmarking in the field, they found out they had chloride profiles in 10 years, which were predicted to be a 100-year profile. A Monte Carlo probability analysis is used with input based on European experience, as noted earlier. The stadium model determines transport of ions in the concrete in both saturated and non-water saturated conditions. It considers a whole slew of concrete properties, as noted here, and it also looks at chemical ionic diffusion without chemical reactions. It looks at the chemical reactions between the ions and the cementitious matrix, and it also can predict the chloride to hydroxide ratio, which in some cases might be a better indication of corrosion initiation, depending on what your cementitious makeup is. It requires determination of non-standardized concrete transport properties, and these need to be performed by a certified laboratory, and the analyses are by certified users. It has been verified in the field, follows the guidelines in both the ACI 365.1R and FIB Bulletin 34. You could apply probabilistic techniques to stadium results. You're not going to run a Monte Carlo on stadium because it takes a day to run each scenario sometimes. So you use something, a Bentz approach or Rosenbluth type technique to approximate what you would get from the Monte Carlo. Long run times and training of the users are probably the major detriments here. The model that we just is developing or starting to introduce is also based on Ficks law. It can analyze overlays and other surface modifications. We can look at effect of cracking on concrete. As mentioned by Doug in the program at Toronto, we do pre-existing chlorides. We have multiple boundary conditions on the same element, so it can be you can have, if you want, we can have a part in water and a part in air. You have 1D, 2D, 3D configurations can be used. The nice part is it uses conventional ASTM and other standard test methods for the concrete properties. Ease of use is similar to Ficks law only models. We verified it under 1D conditions to the other programs using the same input parameters. So it will give the same results if you use the same inputs. While concrete does not become less permeable in time, this can't occur indefinitely. Higher water cementitious concretes could conceivably take longer to reach a constant value, but it's unlikely to be lower than that for the same concrete, a lower water cementitious ratio. So assuming that fusion coefficient will decrease forever in time, will significantly overestimate the time to corrosion. That's important to realize in these models. Stadium and TCG model address this by determining the hydration times. The suggestions on how to do that in Life 365. But we're starting to develop a database so we don't have to wait the time. Why do you worry about this? The mixed specific aging factor can be determined by bulk conductivity resistivity data. So if you would get the fusion coefficient or IDC or whatever you're going to do, and then you would measure relate that to conductivity, and then measure the conductivity change in time on samples that aren't being leached, chlorides, materials aren't being leached out. And you can follow that over time to see what's happening. Duracrete assumes 100 years of hydration. The 365 has 25 years, but that could be changed. And a long-term example that we're going to show shows otherwise for cement and SCMs currently in use. So this is a few of many that we've been testing in our laboratory. The gray line represents normal OPC concrete at a 0.38 water cement ratio. We also had the fusion coefficients, but we're looking at how conductivity changes in time here. And you can see it starts coming down pretty rapidly, and then all of a sudden it starts to average out. So it's really not changing much after 2 years. We think it's going to go up to about 3 or 4 years, and it'll be pretty much constant. Looking at a silica fume and slag mix, we can see it's much lower initially due to the silica fume, and the slag kicks in, and you can see it comes down pretty fast, and it slowly comes down, but by 4 years, it's not changing at all. And we have these on log plots too, and it shows the same thing. It levels off at 4 years. We had a fly ash mix with 0.35 or 30% fly ash. We had some initial data, and then we kind of forgot we had it in the fog room. We came back after a little over 6 years and started measuring the conductivity. And sure enough, at 6.5 years, it's level. So this mix here, which we might be going out to 25, 100 years in some mixes, it's not going to do that. And you're going to have a much different, you won't be very conservative at all on your design calculations if you follow it out that wrong. More problem with the pozzolans, the SCM, how SCMs are treated than in the case of a plain cement. Just to give you an idea of this, looking at how the various models treat this, we have the stadium model, and that gets an IDC, which is related to the fusion coefficient. And you can see that in OPC, at 100 years, it's about 82% of what it started at. So it does come down, but it's not. And then if you have a high SCM content, it's down to 28%. The Life 365 is 31% for OPC and 3.1% for SCM. So it is, compared to stadium, it's making a really large difference with having SCMs here. Duracrete, it's 12% at 100 years for the cement, and it's down into the 1% range for with a high SCM content. The model we have is 52% and 8%, which is a little bit less than a little bit lower than stadium, but higher than the other two. And if this to look at looking for alpha hydration for 100 years, assuming you had a 10K ohm centimeter concrete initially at 28 days, and that's a fairly decent concrete, you're going to be over 1 mega ohm centimeter at 100 years if it keeps following the trend that's there. And I have not seen any concrete anywhere near that. in time. So, I mean, that's just a fallacy of going on too far. Probably should stop somewhere around here, as we indicated. Looking at a service life modeling inputs for a comparison of a few, I'll use a bridge deck in New York. This one actually was part of the Tappan Zee Bridge that was actually mixed being used there. We did a stadium analysis. We used the values from Life 365, and we as defaults for this diffusion. We used the same diffusion all the way across the board for Life 365, Duracrete TCG model. We changed, the slopes were the same for the aging factors in these. However, this would put 25 years for Life 365, 100 years for Duracrete, and 5 years for the TCG model. There was also 2 gallons of calcium nitride in this concrete, but we use this, but our galvanized steel, so we can model either one because they're roughly the same threshold values. When we came around and did the probabilistic analysis, I'll show one such curve is on the right here, and then we have the corrosion initiation time in years. We have the cumulative probability of corrosion damage. Typically, when you hit 10%, in this particular case, that's when it was considered a design life. And you can see that was 129 years here for the TCG model predicted. The stadium model predicted 107 years. Life 365 was, in this case, not very conservative, I would say. It gave 250 years, and the Duracrete gave 350 years. If you looked at all the way over to the 50% side, which is close to deterministic, you can see the stadium is about 151 years, Life 365 is 425 years, 185 years in our model, but 10,000 years, greater than 10,000 years in using Duracrete with 100-year hydration. I just don't believe that. Probabilistic analysis, you can see what does each component play in your O. So you can see exposure concentration, that's 46%. If the exposure is a little more, a little less, that would have a major effect on how long this concrete is going to last. Concrete cover here is 21%. That's because the concrete cover was relatively high. If the concrete cover was a little bit lower, it would be a bigger percent of the variance. In this case, since a minimum value threshold for calcium nitride was used, they didn't have much on the corrosion threshold, did not play a role. And you can see you got 30% noise coming just from the diffusion coefficient. Looking at some advanced modeling we can do, looking at cracks, here we have a case of, actually this is going to be a multi-layered system with, we have an overlay. Here's a control concrete deck with an overlay. An overlay is a silica fume design, a high silica fume design with some fly ash. Then we have a base concrete, which is a little bit higher water cementitious ratio with slag and silica fume. You can see you get out over here at 50 years with the overlay. You're below 500 parts per million with 2 inches of cover. And, for 50-year design, that was quite good back then. We want 100 years now. In 100 years, you're up here, you would need higher cover. If you didn't have the overlay, you can see you're going to have to go out farther in order to be below the 500. And in the case of 100 years, it's just not going to be attainable. So you're going to need some sort of, if you want to go out to 100 years, you need more than just good concrete, a good overlay. And that was kind of shown by some of the results of Doug on some of the silica fume decks where you got very good lifetimes, but if you want to get to 100 years, you're going to need to do something else. So cracking moves all these curves up. So you're going to have a higher, less time to, you're going to need more cover and more help. So you can you can adjust the cracking. And looking for a pre-existing deck, kind of like you have a parking garage, and you can see this is initiations, the blue line, orange is when it goes into, when you have to repair it. Pull the concrete out, now you have no chloride in the top with a new layer in here. And you can model the chloride after time. So the repair in this case would get you up to about 24 years for initiation, maybe a 30-year repair. Simple features are, you can see in the slide, I won't talk over them. They're pretty much, is there. What we are offering in our new system is multi-layer systems, cracked concrete, and then you can look at existing profiles. For the conclusions, so there are several models available, and if you use them properly, they can all give you fairly decent results. The new model we have looks at analysis with overlays. pre-existing chlorides analysis. You can look at cracking using conventional standard test methods for concrete properties, easy to use. I just give a warning that models have long-term reduction diffusion, especially if they have a lot of SEMs in them, as they could overestimate the amount of time that the concrete is going to last. And I'll leave it at that. Thank you.
Thank you very much, Neal. We have a few interesting questions. So for the matter of time, I'm just asking you one question. What is the appropriate acceptance criteria for max crack width and permeable crack densities based on your experience?
Well, what's it now that we have the ability to model it, you can pretty much make it anywhere you want. But clearly, we see a large increase at 0.0. Once you get up to the 0.012 inches or 0.013, where you're talking about minimum ash toe type LRFD criteria, that's going to give you a fair amount of chloride coming in. One or two cracks, you won't necessarily get to your early failure, because so it also matters what the crack density is. So the crack density goes up, you're going to see things going on. Cracks at the 0.07 inches and below, 0.08. If there's not a very high density yet, they only have a moderate effect on the actual long-term life of the structure. You might have a couple spots that show some rusting, but it won't be anywhere near 10%.